Hello, I'm Laura Finzi,
And I'm Kurt Warncke.
and together with our colleague Ivan Raznik, we'll teach the Maymester course, Dynamics of Living System. The course consists of an introductory module on nucleic acids, proteins, and dynamics, and 3 modules on cutting-edge techniques and their application to the study of molecules, to the structure and dynamics of molecules, and the way they determine the function of living systems. Shall we go to the labs and look at the instruments?
Sounds like a great idea.
Okay.
Electron magnetic resonance is a technique that detects single electrons. Single electrons behave as tiny magnetic dipoles, much like the north-south dipole on a compass does. You know, the compass from experience aligns with the external magnetic field of the Earth, and it's a similar situation with the electron magnetic dipoles in a sample that we study. These dipoles are localized on biological molecules, and they report on the physical properties of that molecule. As an example, these tiny bar magnets could represent the electrons in the sample. And what we do to organize them is put them in a powerful magnetic field so that they all orient in the same direction. Okay? Then we come in with a second magnetic field from a microwave radiation source, and we randomize those magnetic dipoles and make them execute motions, and we detect those motions, and that detected motion gives us the environments of the electrons, which can report on the neighbors of the electrons, the molecules, and the structure that surrounds them. And that's how we gain information about the biological system at the nanometer scale. So we've talked about the classical analogy of bar magnets and magnetic fields on a tabletop, but let's see what that really looks like at the molecular level. So if we look up here, we see a representation of the protein that we study. It's called a ribbon diagram. And the molecules that have the unpaired electron reside inside of this protein. If we go down here, we see the more of the space-filling aspect of the protein presented. And these green sticks here represent the molecules in which the unpaired electrons reside. So this is what we probe inside the protein. To give you an idea of the scale here, the width of this protein is about 4 nanometers. That's 4 billionths of a meter. So let's go and see what we find out from applying the electron magnetic resonance technique. What we are able to acquire in principle is a 3-dimensional representation of the molecules inside the enzyme. And the enzyme that we study happens to be the vitamin B12 enzyme. And this is what vitamin B12 looks like as a molecule and as it sits inside of the protein. Our measurements show the distances between the atom centers that have the unpaired electron spin on them, for example, a cobalt, and this is a substrate radical. The distance between them is 11 angstroms. We can measure that with our method. Furthermore, we can measure the distances on the scale of tenths of nanometers between the unpaired electron and nuclei in the environment. This information is vital for determining the catalytic mechanism of the enzyme. Next, we'll go and have a look at the equipment that performs these measurements. Here we are in front of the instrument that makes the measurements. This is called a pulsed EPR spectrometer. This is the electromagnet, pole faces, that we use to polarize the electrons in the sample. In other words, align them along certain directions so that we can manipulate them. The sample is held inside of this cryostat, which keeps the sample at a constant temperature. And over here, we have the electronics that are involved in producing the pulse magnetic field that interacts with the electrons and manipulates them, and also the instrumentation that acquires the signal from the electrons. That signal is then transferred to a computer where it is stored and later analyzed, and that generates the interpretation of the data in terms of the molecular structure of the system. So in the electron magnetic resonance portion of the Maymester course, you will learn about all of the aspects of the acquisition of the data, the interpretation of the data, generation of a molecular picture of what the inside of a protein looks like.
This is a different application of magnetism to the study of biomolecular function. Here we have a microscope equipped with magnetic tweezers. Magnetic tweezers are these two little magnets that you may have difficulty in seeing that are placed right above the stage. The magnets can be moved up and down along the optical axis of the microscope or rotated. On the stage of the microscope, we place a microchamber, just like this, a tiny microchamber, where we flow in DNA molecules and proteins. Now, these DNA molecules are attached at one end to one surface of the microchamber and at the other end to a magnetic bead. With the magnets, we can pull on the beads and stretch the DNA. That way, we can study the elastic properties of DNA. Or we can rotate the magnets, therefore rotating the beads and twisting the DNA molecule. The twisting generates supercoils, which are these loops. These loops that are formed if you overwind or unwind the DNA molecule. Now these loops, these supercoils, mimic the supercoiling that is actually naturally occurring in the cell, and which regulates the interaction with many regulatory proteins. So this is what we study. We study DNA-protein interactions as a function of supercoiling and tension. And this machine, this microscope, allows us to do that. The beads are visualized on the screen of a computer. We don't see the DNA. The DNA is invisible, but we do see the beads. And we can record their height with respect to the surface of attachment. And we can record their rotation. So if you come in May, you'll learn more about magnetic tweezers, the way they're built, the way they function, the way they are applied, what type of questions you can ask with magnetic tweezers, as well as other techniques. You will learn about the tether particle motion technique, atomic force microscopy, and their applications. I hope to see you next.
We hope you've enjoyed this brief tour of our Maymester course, Dynamics in Living Systems, and we look forward to showing you more in May.
Bye.